Welcome to the next session, and in the first talk here we're going to hear about how to make cons-free programming, not cons-free.
That's right.
So welcome, Siddharth, Bhaskar.
Thank you very much. Thanks everyone. So my name is Siddharth. I'm at James Madison University in Virginia, and I'm going to be talking about some work that I did when I was a postdoc at the University of Copenhagen with Jakob Simonsen. And I should start out by saying that I am not, so this work combines sort of programming languages and computational complexity. I am neither a programming languages nor a complexity person. So my background is in mathematical logic. I will be talking about programming languages without knowing anything about them, which should be apparent almost immediately, but we'll see how it goes. So RW-factorization, that's read-write factorization, and I want to start by introducing what does this even mean? Okay, so I'm going to define a simple first-order language over strings. So let's fix an alphabet sigma. So by an alphabet, I just mean a finite set of size at least 2. Sigma star is a set of finite sigma strings, and that's the only type that this language has, except for the set of booleans, which we call 2. And we're going to consider the following set of string primitives. Okay, so we have head and tail, which decompose a string into its first character and the remainder. Nil, which is a constant naming the empty string. Null, which is a test whether a string is empty. And cons, which basically smushes a character onto the front of a string. And how do we build a language from that? Well, I'm going to form terms from basically recursive calls and calls to the primitives, the string primitives, which are those, and conditionals, if-then-else statements. And then a program is just a list of simultaneous recursive equations, which we can endow with least fixed point semantics or whatever we like. So this is the kind of program I mean, right? I've seen concatenation written on these screens many times today, so here's another one. So to concatenate a list, you test whether the first string is empty, and if not, you concatenate the tail of the first string with the list and smush the head onto the front, right? And I've also seen reverse several times on these screens, and here it is again, or one version of reverse, right? To reverse a list, you recursively reverse the tail and then concatenate it on the other side with the head. Okay, so this is certainly a very plain Turing-complete programming language, and I want to remark that its running time, that is like the time native to this language, is basically identical, I think, to time on a deterministic Turing machine, which is to say we can compile each model to the other in a way that basically preserves time. So now I want to say what I mean by a cons-free program. Okay, so amongst these string primitives, head, tail, and null are destructors, right? We use them to decompose a string, and nil and cons are constructors. So we omit the constructors to get cons-free programs. And obviously this is no longer a Turing-complete language, and it seems like a very weak one, right? What can we even do here? And it's sort of a, by now, classic theorem of Neil Jones that cons-free programs, if we're looking at programs which compute relations, so functions of type string to Boolean, these compute exactly the class of polynomial-time relations, right? So in other words, every polynomial-time relation is computable by a cons-free program of the appropriate type, and every cons-free program of the appropriate type computes a polynomial-time relation. And if we restrict ourselves to the tail-recursive fragment of this language, where every recursive call is in the tail position, then we capture logarithmic space in exactly the same way. And moreover, this was sort of extended by higher types into a correspondence which captured levels in the deterministic exponential hierarchy. So for example, x prime, 2x prime, like, you're looking at finite towers of exponentials, and their union is the class of elementary functions, right? So that's if you have sort of unbounded order. So from this whole program, as you can see, it's sort of a useful framework for capturing a number of robust, complex, deterministic complexity classes of interest. And there's a number of outstanding questions, so two of which are, what is cons-free running time? So the running time of the original Turing-complete language basically corresponds to Turing machine running time, but when we remove cons, we sort of severely lessen its power, in the sense that, yes, we can compute every p-time thing by a cons-free program, but the cons-free program may itself run in exponential time. And then the other thing is, how do we capture functional complexity classes? So not just relational, but functional. So obviously, without constructors, we can't even capture the simplest of functions which increase the input. And so these are two questions, the two questions which I basically solved in my postdoc. And the current paper, or the present talk, is about the second question. But the first question is a previous paper, and it's really part of one story. So I do want to say this, which is very interesting. Cons-free running time is the log of Boolean circuit depth. So we remove cons from the programming language, and we actually recover another classic measure of complexity, which I think is very interesting and unexpected. And so that means, this is also joined with Jakob and Jakob, and this means that we have characterizations of complexity classes like NC, which is intermediate between L and P, as a time class of cons-free programs. Okay, so we're going to come back to this result at the end of the talk, but for now, let's focus on the second question, which is how to accommodate polynomial time functions in this framework. Okay, so obviously we have to use some sort of construction, but how do we use it in a limited way? So cons-free programs, we can think of them as having just one type of data besides Booleans, which is read-only strings. So the basic idea is to augment programs with a type of write-only strings, right? Strings that you can only construct. So you can't have strings that you both construct and destruct, but with a typing system, we can sort of partition all of our strings into construct only and destruct only, or write only and read only. And once we do that, we get the following typing of the string primitives, right? So head, tail, and null sort of operate over R strings, and then nil is a string of type W, it's the empty string, and cons works on write-only strings of type W. So we have some sort of typing discipline which we can impose on programs, and we say a string program is RW-factorizable if its recursive function symbols can be consistently typed in this way. So if we look at the previous two examples of concatenation in reverse, we can see that they can in fact be typed this way, right? So for concatenation, it's important that the first variable is a read-only variable, which we destruct, and the second variable is a write-only variable, which we construct. And then reverse is just a function from R to W. And if you go through this syntactically, you can check that this typing is correct. Now, here's an example of a function or a program which is not consistently typable. It basically takes, so here 1 is just a character, it's a numeral, not the number 1. It takes in a string, and the output is a string of 2 to the length of the input ones, right? So you take in a string of length n, you return a string of 2 to the n ones, and it's basically, just a standard sort of definition of the exponential function, binary exponential, just hidden a bit. But you can see that it's not consistently typable because we feed the same term into both arguments of concatenation, which are typed differently. Okay, so one might suspect then that we're done. RW-factorizable programs of this type exactly capture polynomial time functions. Unfortunately, that's not quite correct. So here's an interesting program, which I call LEAP. And it's sort of hard to describe exactly what it does intuitively, because there's a nested recursion going on here, right? The second recursive call is, or the second line is f of tail of x, comma, f of tail of x, comma, w. And I would love to, if I would have a board and work some small examples out. But if you do so, you'll actually see that this function computes exactly the same thing as before, right? But it's eminently RW factorizable, right? You can absolutely type it. And I have one of the W arguments here in red, which is a typo. It should be in blue. Okay, and this is clearly not a polynomial time function because the output is too large. But it turns out that if we eliminate nested recursive calls, we get exactly what we want, right? So non-nested recursion, polynomial time functions are exactly captured by non-nested RW-factorizable programs of this type. And moreover, if we restrict to the tail recursive fragment, we recover log space functions in exactly the same way. Here we don't need to say non-nested because the tail recursive property already covers that for us. And you might wonder why the original theorem of Neal-Jones didn't have the non-nested assumption in it, and that's because in cons-free programs we can actually eliminate nested recursion. Okay, so before I get in, I want to say something about the proof. But I sort of want to say a little bit first, a bit of an aside of why I think that this is sort of a robust idea, which goes beyond like this particular like language. Like obviously you can talk about RW factorizability for programs over any type of data which can be, whose primitives can be partitioned into constructors and destructors. But if we think about it even more generally as sort of an algorithmic paradigm, like let's look at some sorting algorithms. Like I think it's instructive to like think about how this concept can be used to sort of maybe give a taxonomy to various algorithms. So insertion and selection sort are vaguely RW factorizable. And I say vaguely because if you think about it hard enough, you'll realize that they're actually not, or insertion sort isn't, according to the type discipline which I just talked about. But if you don't think about it too hard, well then they basically like can destruct the input and they construct some sorted output, right? Okay, so, and I think that they should be in some sense. So like maybe my definition isn't quite general enough or something, but they should be. Now let's think about heap sort. Now heap sort is not RW factorizable because we have this datum, the heap, which we're both constructing and destructing. However, we can express it as a composition of two RW factorizable procedures. Again, vaguely RW factorizable procedures, right? In one, we sort of have a list and we destruct it while we construct a heap. And then in the next part, we sort of do the opposite. We have a heap, we destruct it, and we construct it into a sorted list. So, okay, it can be expressed as a composition of two things. And now let's think about merge sort. Now, when you're, just the merge operation definitely is literally RW factorizable. We are destructing two read-only lists and we construct an output list. But merge sort itself is not, right? And I think not in a very strong sense because there's no way, right here you can see that the input type and the output type of the sorting function has to agree with, the output type of msort has to agree with both the input and the output type of merge. And I think that if you, I think that sort of construction and destruction are sort of hopelessly entangled in merge sorting. And so I just wanted to air this out as like, does this suggest sort of, is this a profitable way to think about algorithms? Okay, so that's sort of one deeper question, but let's leave that aside for the following time and talk a little bit about the proof. So in the proof of the original correspondence, cons-free programs with polynomial time relations, a crucial part of the machinery was counting modules. So counting module is basically a dependence type. It's an initial segment of the natural numbers, which is bounded by some polynomial in the length of the input. So it depends on the length of the input. And this is very useful when you're trying to simulate p-time Turing machines because the counting modules can be used to measure the time, like running time or the length of a work tape or whatever. And the nice thing is that counting, if you extend cons-free programs by counting modules, it's a conservative extension. I don't know what the correct PL term is, but by conservative extension, I mean maybe you can compute functions of more types, but of the functions that you could compute, like if you're looking at functions of the same type as a ground program, you're not extensionally computing more things, right? You can eliminate them. A counting module basically can be eliminated in favor of a fixed width tuple of read-only strings. And the idea is very simple, right? If I have an input of length n and I want to get numbers up to, let's say, n cubed, then what do? I just represent it as a triple of numbers less than or equal to n, right? A 3-digit number base n, and a digit base n could be encoded by a suffix of the input string, which you can get by taking tail. Okay, and so we're going to use these counting modules. So Neil in his original paper used counting modules but didn't formulate them as a dependent type explicitly. But actually formulating as a dependent type explicitly is very useful because we can now extend his original theorem by additional types. So basically, by 1 star, I mean the natural numbers, right? Unary strings. And functions of type sigma star times 1 star to Booleans and sigma star to 1 star and other types involving 1 star are computable in polynomial time if and only if they're computable by cons-free programs with counting modules. And the idea here is that the counting modules handle unary strings in 1 star. And there are essentially no new ideas here. It's just modifying the proof from before to handle these additional types with the additional type that we have. Okay, so what does that have to do with computing functions from strings to strings, right? Because that's what we really care about. So if I have a functions from strings to strings, I can sort of decompose it into 2 functions, the bits function and the length function. So the bits function over here sort of tells me, like I have my string, and you should think about this as an index, and this returns the character at that index. And the length function takes a string and returns its length, right? And from a function from strings to strings, I can define this, and vice versa. If I have this, I can define the other thing. And the observation is that f is computable in polynomial time if and only if its bits and length function are, which immediately gives us a characterization of that a function is computable in polynomial time if and only if there are cons-free plus counting module programs which compute its bits and length function respectively. Okay, and this is just immediate from a minor extension of Neil's original result. And all of this holds respectively for logarithmic space and tail recursion. Okay, so how do we show the capturing by RW-factorizable programs? Well, simply we provide a compilation in both direction between RW-factorizable programs and pairs of cons-free programs with counting modules, bit length computing, the bits and the length of the original function. And here's just sort of one tiny part of one of those program transformations. If I'm computing the identity function, right, reproduced over here, so the identity function is I recursively compute the identity of the tail, and then I smush the head in front of it. Then I can compute the length of the identity function in the following way. It's just 0 if the string is empty, otherwise it's 1 plus the length of the identity function on the tail of x. And you can sort of see how you can get the bottom one from the top one via a program transformation. The structure is sort of similar. Of course, it's more complicated to do the bits function, and it's, you also have to go in the other direction, but that's just a hint of what's involved. By the way, I should remark here that you do have to do something like this to get an RW-factorizable identity function. Just the trivial program ID of x equals x is not typable of type R to W. Okay, you have to deconstruct the input and construct the output, which shows you information can flow from R types to W types, but you have to do a little bit of work to do so, and you can't go in reverse. Okay, so now I want to talk about compositionality. So RW-factorizable programs are not naturally compositional because, well, R and W are not the same type, right? So what if you wanted to sequentially compose them? And I think that this is a feature because if we remember heap sort, it's the composition of 2 RW-factorizable procedures, but is not in and of itself RW-factorizable. And that captures something about the intentionality, the intentional meaning of heap sort, right? We don't want the whole thing to be RW-factorizable, but we do want to be able to compose these things. Bit length programs are, however, loosely compositional in the sense that we're basically using the same sort of information about, we're taking the bits of the input using the head function, for example, and we're defining the bits of the output, right? So we're using the same type of things for the input and the output, which means that there's a relatively simple program transformation composing these guys, pairs of bit length programs, and we can lift that to something. We can lift that to something composing RW-factorizable programs. Okay, so I want to say some consequences, and I'll move a little bit more quickly here. But one is because you have these program synthesizing functions, like we can compose them efficiently. We can actually show that these programs satisfy Kleini's second recursion theorem. And I don't know that it's sort of known that Kleini's second recursion theorem follows from the existence of various program synthesizing things, but I don't know that it's been studied for sort of sub-recursive programming languages before. Okay, so there's some nice things, but I want to end with this talk. I want to end this talk by talking about some big questions. So first of all, I want to dedicate this talk to Neil Jones, who passed away suddenly earlier this year. Neil grew up basically coincident with the physical computer. He was born in 1941 and started programming as an undergraduate in Southern Illinois University in the early 60s, if not the late 50s. And always thought that complexity and PL should talk to each other. And if you knew anything about Neil, is like very allergic to being pigeonholed. So here's a bunch of blended complexity PL questions, which I think are very interesting. In the interest of time, I think I'll just present one, which is not this one, but this one. How many languages, how many programming languages are there? Well, just one in the sense that there's a single indexing of the partial recursive functions up to isomorphism, right? So this doesn't say much. It says that we can computably compile any Turing-complete programming language into each other. But how many languages are there which capture p-time? I've just presented one, but there's a host of other so-called implicit characterizations of polynomial time. Are they the same, obfuscated a little, or are they genuinely different? So how many indexings are there up to polynomial time isomorphism? Right, and there's sort of three choices, right? Finitely many, countably many, or continuum many. And I have no idea sort of which world we're living in, or if it even depends on complexity theoretic hypotheses. So this is something I'm very much interested in, and I think sort of blends PL and complexity theoretic characterizations. There's a couple other big questions and that I'd be happy to talk about offline, but maybe I'll stop here. And thanks very much.
All right. Do we have any questions? And remember to state your name and affiliation.
Hi, I'm Felix Klock. I'm not 100% familiar with all the work you showed, so I'm just going to ask a very direct question about a detail you showed.
Sure.
You mentioned that the bit about some property being logarithmic in the Boolean circuit. The length, length of the Boolean circuit.
Yes.
I'm trying to figure out, is the intuition there that the program is going to, the ideal program here that's going to accomplish that logarithmic complexity is going to be evaluating in parallel, I'm trying to figure out how you get logarithmic at the length. And I'm assuming it's about jumping halfway down and having them both run in parallel and do that repeatedly. Is that the intuition?
So circuit depth is log of const-free running time, right? So const-free running time is a bigger one. Circuit depth is a lower one.
Okay.
What we actually do is, instead of using circuits, we compile them to aux PDAs, which are push down automata with the stack, and the depth of the stack, I think it is, or is it the running time, is the resource which captures const-free time, and that is known to be something like the log of circuit depth.
Oh, okay.
So I just said circuit depth because I thought that would be the more familiar measure.
Okay, thank you.
Thanks very much.
Hi, Neil Krishnaswamy, University of Cambridge. Thanks for a very interesting talk.
Thanks.
So one question I had was the type system you imposed on these programs was quite simple.
Yes.
And I wondered if you had thought about perhaps if you used some restrictions like linearity, if there were any way to intertwingle read and write a little bit more.
Yeah, I haven't, but mostly due to my own ignorance. But I would love to sort of learn more and see how they interact, because many of the other characterizations have to do, like implicit characterizations have to do with linearity. And I wonder if that's somehow encoded here or something like that. Yeah, I would love to learn more.
Okay, thanks.
Thank you.
All right, let's thank our speaker again.
Thank you very much.